Hey everyone, this is part 3 of lesson 7, and so before we were talking about graphing things in the polar coordinate system, and now we're going to go to a related topic, complex numbers. So you might remember complex numbers from algebra, and those are those numbers where we have something plus something times I. Alright, and sometimes you might hear those called imaginary, but we like to call them complex numbers. So any of these numbers of the form a plus bi can be graphed on the complex plane. And by the complex plane, we basically just mean the xy plane, but we're going to have a real axis and an imaginary axis instead of an x and y axis. So the horizontal axis is the real axis, and the vertical axis is the imaginary axis. So basically what this means is that any number a plus bi will correspond to a point AB in the xy plane. So you graph these just like you graph ordered pairs. So we're going to practice with a couple of examples. So first of all, we're given the complex number z1 is negative 2 minus 3i, and z2 is 3 minus I. So we'll graph those first, and then we'll worry about the sum and product. So let's divide up our axes into 10 notches. I think that's 10. Yeah. So let's do that. And let's do 7 on the vertical. So to graph the point negative 2 minus 3i, that's going to correspond to the point negative 2 comma negative 3. So all we have to do is go to the left 2 units and down 3 units, and that will be the point z1. All right. To graph the point 3 negative I, this will correspond to the point 3 comma negative 1. So we'll go to the right 3 units and down 1 unit, and that will be z2. So now if we want to add our two numbers, so if we want to do z1 plus z2, all we have to do are add the like terms. So z1 plus z2 is the same as negative 2 minus 3i plus 3 minus I. So if we want to add these like terms, we get that negative 2 plus 3 is a positive 1, and negative 3i minus I is a minus 4i. So the sum of our two complex numbers is 1 minus 4i, and that's the same as the point 1 comma negative 4. So to graph that point, we just go to the right 1 unit and down 4 units. And so this is the point z1 plus z2. Okay, and to find the point z1 times z2, we simply have to multiply the two numbers. So z1 is negative 2 minus 3i, and z2 is 3 minus I. So if we multiply these two things together, remember that when we multiply two complex numbers, it's pretty much like foiling a polynomial. So we get negative 2 times 3 is negative 6. Negative 2 times negative I is a positive 2i. Negative 3i times 3 is a minus 9i. And negative 3i minus I is positive 3i squared. Now, remember to simplify this that since I is the square root of negative 1, we can say that I squared is equal to negative 1. So anytime that an I squared pops up in your computations, you can always substitute that with a negative 1. So combining the like terms, we get negative 6 minus 7i plus 3 times negative 1. So finally, we get negative 6 minus 7i minus 3, which gives us negative 9 minus 7i. And that will correspond to the point negative 9 comma negative 7. So we count 9 units to the left and down 7 units, and that'll kind of get in the way here, but this will be the point z1 times z2. Alright, so that is how you graph complex points in the complex plane. So we're going to do another example here, and this is not graphing just a set or a particular number. Instead, we're going to graph an infinite set of complex numbers. So here what we need to notice is that we're defining a to be between 0 and 5, and we're also defining the absolute value of b to be less than 3. So first of all, just to clarify, this is the a-axis and this is the b-axis. So a is kind of like the x-axis and b is like the y-axis. So if we divide up a into, we'll just do like 6 units or 7 units, that should do us. And so that'll be good for a. And for b, let's remember what the absolute value means. So if the absolute value of b is less than 3, that means that b is between -3 and 3. So if you take the absolute value of anything between -3 and 3, then you would get something less than 3. So that's how we arrive at this definition of b. Okay, so we need to divide b into at least 3 units on each side. So looks like we got 5 in there. Alright, so that should be good for our b-axis. So now we need to go ahead and graph our set. So if you remember, when graphing inequalities, if we have an inequality with an equal sign, like a less than or equal to, like we have here, we use a solid line. So we have that a is greater than or equal to 0. So that means that our first vertical line is going to be at a equals to 0, and that is the b-axis. Okay, we also know that a is less than or equal to 5. So at a equal to 5, we're going to have our second solid line. So it'll look like this. All right, so we've taken care of the a. Now we need to take care of this b condition right here. So remember we said that we need b in between -3 and 3, but notice this time we don't have an equal sign on our inequality. So what this tells us is that we need to use a dotted line. So at +3, b equal to +3, we're going to have a dotted line. All right, and at -3, we'll have the same thing. We'll have another dotted line. All right, so now all we have left to do is shade in the region that agrees with all of our inequalities. So if a is between 0 and 5, we're going to be between those two solid lines. But if b is between -3 and 3, we're also going to be between the two dotted lines. So what we've kind of done here is define this rectangle, and that's going to be our solution. So anything inside the rectangle is the set that we defined at the top. So it's all the complex numbers z that satisfy that property for a and that property for b. All right, so that's just a few examples of the different ways you can graph complex numbers. All right, one important concept when we talk about complex numbers is its absolute value or its distance from 0, 0 on the plane. So if you remember, absolute value is kind of like a number's distance from 0, and that's why it's always positive. So when we talk about a complex number, we talk about its distance from 0, 0 because we're in 2 dimensions. So another name for the absolute value is the modulus of z, but the notation is the same. So notice we put z inside of those absolute value bars, and this is simply the square root of a squared plus b squared. So you can kind of think about this like Pythagorean theorem. So let's say we have some point, a plus bi, somewhere in the plane, and we want to find the distance from that point to the origin. So that is going to be our modulus z. Okay? And we know that the vertical distance of this triangle, we're going to kind of make a right triangle here with the x-axis. So the vertical distance is b, and the horizontal distance is a, and that just comes from the fact that we're graphing the point AB. So how would you find the hypotenuse of that triangle? Well, since it's a right triangle, and we made it that way, we can just use Pythagorean theorem. So we know that a squared plus b squared should give us z squared. And if we wanted to solve for z, we could just square root the whole thing. So we get that z is equal to a squared plus b squared inside of a square root. All right? And because we're talking about a distance in particular, we want to make sure that that distance stays positive, and that's why we add the absolute value bars. So we can say that the modulus of z, or the absolute value of z, is the square root of a squared plus b squared. All right, so hopefully that makes a little sense, but we're going to practice with a couple of examples on some numbers next. So we want to find the modulus of each complex number. So for the first example, we have z is equal to negative 3i. So we can kind of think about this as 0 minus 3i, in case you're wondering where that a number is. So if we wish to find the modulus of z, we know that that's the square root of a squared plus b squared. So we can plug in our values for a and b. So we have the square root of 0 squared plus negative 3 squared. And if we simplify this, we get the square root of 9, which is 3. So in the case of square roots, when you're finding a modulus, always assume the positive square root because we're looking for a positive number to be the modulus. Okay, so that's how we get a positive 3. Now in the case of the second example, z equals negative 2 plus 5i, it's going to be a little more complicated, but it's the same formula. So we have the modulus of z is equal to the square root of a squared plus b squared, which is the square root of negative 2 squared plus 5 squared. So if we simplify this, we get the square root of 4 plus 25, and that is just the square root of 29. Now 29 is a prime number, so it doesn't have any factors that could possibly be perfect squares. So that is the simplest form of that radical. Now keep in mind, if you did get a radical that was not in simplest form, like let's say you had the square root of 56, for example, you would want to simplify that. And to do that, you would find the prime factorization of 56. So we could write this as 2 times 28, and we could split 28 into 4 and 7, and we could split 4 into 2 and 2. So all you do to simplify the radical is just figure out what pairs of numbers you have. So you want to circle your pairs and box your things that are by themselves. And so what happens is anything in a square stays under the square root. So we have the square root of 2 times 7, which is 14. And on the outside, we just take one of the numbers from the pair. So the square root of 56 would just be 2 times the square root of 14. So that's just a little review on how to simplify square roots. But in this case, it's not necessary because, as I said, 29 does not have any factors that are perfect squares. All right. So now that we've talked about the modulus, let's tie this into our polar coordinate system. So one really handy form of a complex number is its polar form. All right. So a, which you can relate a to x, sort of. So that's the same thing as r times the cosine of theta. B you can think of as y from the last section, and that's r sine theta. Furthermore, we can say that r is the square root of a squared plus b squared, and theta is the inverse tangent of b over a. So it's the same formulas as in the last section. All we're doing is replacing x and y with a and b. So any complex number of the form a plus bi, we can sub in those formulas for a and b into a plus bi. So what we get is r times the cosine of theta plus r times the sine of theta times I. And we can further simplify this by factoring out the r. So we get that it's r times cosine theta plus I sine theta. We usually write the I before the sign just so we don't get it confused with the theta. So I is outside of the sign. And furthermore, if you wish to use a simplified notation, and I'll actually use this a lot because I think it's really handy, you can shorten this to RCIS theta. So CIS is just a shortened version of cosine I sine. All right? So, if you wanted to graph this, it would be like you do in the polar coordinate system. So, you have some radius out from 0. So, like, let's say we had a radius somewhere right here, and you would rotate that some angle theta. So, let's say that your z was here. So, you would have some r and some theta, and that's how you would graph a point in its polar form. Okay, now the modulus of z is represented by r. Hopefully you realize that from the formula up there. Furthermore, we have what we call the argument of z, which is just theta. So the theta from this RCIS theta is called the argument of z. So let's practice finding the polar form of a number. So we are given z is equal to -2 minus 2 times the square root of 3 times I. So first what we want to do, and you don't have to do this in the future, but I think when you're starting out it's really handy. So first we want to identify a, and so a is -2, and then we want to identify b. B is -2 times the square root of 3. So a is just the constant term, and b is the term with the I. All right. Now, one other handy thing to figure out is what quadrant this number would be graphed in. So because both of our coordinates are negative, we can say that this would be in quadrant 3. And that will come in handy when you do the inverse tangent later. So next what we want to do is find the radius. So we know that r is the square root of a squared plus b squared. A is -2, so we have -2 squared plus -2 square roots of 3 squared, which if we simplify this is the square root of 4 plus 4 times 3, which is the square root of 4 plus 12, which is the square root of 16, which is just 4. Alright, so we have our radius, and the last thing we want to do is just find theta. So theta is the inverse tangent of y over x, or a b over a. So we have the tangent inverse of -2 square roots of 3 over -2. And if we simplify this, we have the tangent inverse of the square root of 3. And so now we just need to think about what angle in quadrant 3, so this is where the quadrant comes in really handy. So what angle in quadrant 3 has a tangent of the square root of 3? And an equivalent question is, since tangent is sine over cosine, our equivalent question is, what angle in the third quadrant has a sine of the square root of 3 over 2? Or negative square root of 3 over 2. And the angle we get is 4 pi over 3. So that is going to be the argument of our complex number. So the only thing we have left to do is write out the full polar form of this number. So we have the radius. So remember, this is RCIS theta. So we have 4 CIS 4 pi over 3. So that is the polar form of this complex number. Okay? Now our next example, we have a complex number that's already in polar form, and we want to change it to our regular a plus bi form. So there should be a bracket right here. Apologize about that. So here, what we want to find are a and b. And we know that a is equal to r times the cosine of theta, And we know that b is equal to r times the sine of theta. So all we have to do is plug in our values. So we have square root of 8 times the cosine of negative pi over 3, which is, if we wanted to simplify the square root of 8, that's just 2 times the square root of 2, and the cosine of negative pi over 3 is 1/2. So if we multiply 2 square roots of 2 times 1/2, the 2's cancel out, and we just end up with the square root of 2. Alright, for the b number, we have 2 square roots of 2, so again I'm just substituting that instead of the square root of 8 because that's the simplified form, times a negative square root of 3 over 2. So that is the sine of negative pi over 3. And if we simplify these two things, we have 2 and 2 cancel out, so we end up with negative square root of 6 as our b. So the last thing to do is just write this in a plus bi form. So a plus bi then is equal to the square root of 2 minus the square root of 6 times I. And so that is the rectangular form of the complex number. Okay, so now that we've talked about the polar form of a complex number, the next thing we want to talk about is, well, how can we multiply and divide things in this polar form? Because that's the whole point of putting complex numbers in polar form. It makes multiplication and division a lot easier. You don't have to worry about the I squareds floating around. You don't have to worry about getting like terms to combine. It's really, really simple. So I have some formulas up here, and yes, they look complicated, but basically to multiply two complex numbers, you multiply their radiuses, or their radii. So this is the same thing as R1, R2, CIS, and you add their arguments. So all it is multiplying the radii and adding the arguments. That's not too bad. So division, you can also think of similarly. So basically all you want to do is divide the radii and subtract the arguments. So that's a simpler form of that equation. So I told you that CIS notation comes in really handy. Alright, so that is all there is to it. And to me, that's a lot easier than rectangular form, you know, having to remember to multiply all those terms and everything. So this is a good thing to know. So let's practice with a concrete example. So if we want to do z1 times z2, and we have z1 is 2 times the cosine of 2 pi over 3 plus I sine times 2 pi over 3. So we can rewrite this as 2 CIS 2 pi over 3, just for ease of notation. And the second one we can rewrite as 8 CIS 11 pi over 6, just for ease of notation. So z1, z2, we know is r1 times r2, and the 1 and 2 just refer to the 1 and 2 in the z respectively. So we have r1, r2, CIS, theta 1 plus theta 2. So r1 is 2, r2 is 8, and we have CIS 2 pi over 3 plus 11 pi over 6. Okay, and if we add these together, we get 16 CIS, and if we get common denominators here, we get 4 pi over 6 plus 11 pi over 6, which is 16 CIS 15 pi over 6, which if we simplify that now, we get 16 CIS 5 pi over 2. So that's the polar form. Now, if we wanted to change that back to rectangular form, as we often do, we can think about this as its expanded form. So we have 16 times the cosine of 5 pi over 2 plus I times the sine of 5 pi over 2, which if we simplify the cosine and the sine, we get 16 times 0 plus I, and if we were to distribute 16, we would just get that this is 16I. So to me, that's a lot easier than FOILing out, but you're welcome to do it either way, unless I ask you on a test, like use the polar form to multiply these two numbers. So anyway, that's just another way to multiply two complex numbers. So now let's talk about division. So division is really similar, except instead of multiplying the two radii, we're going to divide, and instead of adding the two arguments, we're going to subtract. So z1 over z2 is r1 over r2 cis theta 1 minus theta 2. So this comes out to be 2 divided by 8 cis 2 pi over 3 minus 11 pi over 6. Alright, and if we simplify this, we get 1/4 cis 4 pi over 6 minus 11 pi over 6, which gives us 1/4 cis negative 7 pi over 6. So again, this is the polar form, but what we want is the rectangular form. So we just need to write this in its expanded form and simplify. So we have 1/4 times the cosine of negative 7 pi over 6 plus I times the sine of negative 7 pi over 6. And if we simplify that, we have 1/4. The cosine of negative 7 pi over 6 is negative root 3 over 2. And the sine of negative 7 pi over 6 is 1/2. So we've got this going on, and all we need to do now is just distribute the 1/4. So if we multiply the negative root 3 over 2 by 1/4, we get negative root 3 over 8. And if we multiply 1/2 by 1/4, we get a positive 1/8 I. So that is the rectangular form of that original polar answer that we got. Alright, so again, those are just the polar way to multiply and divide complex numbers. So now we want to look at something called De Moivre's theorem, which basically tells us how we can find powers of complex numbers really quickly using the polar form. So it says if z is in its polar representation, then z raised to some power, all we have to do is raise the radius to the power of n, and we have to multiply the argument inside of sine and cosine by n. So this is where the polar form comes in extremely handy, because we don't have to sit here in this example and multiply negative 1 plus square root of 3i by itself 12 times. All we have to do is convert it to its polar form and use this really nice theorem, and we're good to go. So let's work on this example. So first we need to change negative 1 plus the square root of 3i into polar form. So to do that, the first thing we need is its radius. So the radius is the square root of negative 1 squared plus the square root of 3 squared. And so if we simplify this, it gives us 1 plus 3, which is the square root of 4, which is 2. Sorry, that shouldn't be a plus. It should be an equals. Okay, so our radius is 2. And to find the argument, we just need to do the tan inverse. So we have the tan inverse of the square root of 3 over negative 1. So tan inverse of negative root 3. Now, again, remember I said figuring out what quadrant this is in is important. So if this is the point negative 1 square root of 3, we know that this is going to fall in quadrant 2, because the x-coordinate is negative and the y-coordinate is positive. So if this falls in quadrant 2, the way that we get our angle is we think of what angle in quadrant 2 has an inverse has a tangent of negative root 3. And the angle that comes to mind is 2 pi over 3. So our argument is 2 pi over 3. So the polar form of this number is, so we can say that negative 1 plus the square root of 3 times I is equal to 2 CIS 2 pi over 3. So that's a really nice way to write that number. And so now we can use de Moivre's theorem to expand this out really nicely. So if we want to find, so z is equal to that, so if we want to find z to the 12th, all we have to do is take our radius, raise it to the 12th power, and multiply our argument by 12. So it looks like this. And furthermore, if we wanted to simplify this, we can put 2 to the 12th into a calculator, and you should get 4096, and then CIS, and if we carry out this multiplication, we should get 4 times 2 pi, which is 8 pi. So the polar form of z raised to the 12th power is 4096, CIS 8 pi. So if we want to put this back into rectangular form, we can think about expanding it. So we have 4096 times the cosine of 8 pi plus I times the sine of 8 pi. Now the cosine of 8 pi is 1, and the sine of 8 pi is 0. So if we were to go ahead and distribute this out, we would just get that our answer is 4096. Okay, and to me that is a lot easier than multiplying this number by itself 12 times. So if you thought that the multiplication division, well, it didn't save you that much time, I promise you this will save you a lot of time. So keep that in mind. It'd probably be a question on your test. So if we talk about raising complex numbers to powers, our next question is, well, how can we take an nth root? And so we have a similar idea for taking nth roots. So if we have z in its polar form, then our number actually has n distinct nth roots. So this means if you have cube roots, you have 3 of them. If you have square roots, you have 2 of them. If you have fifth roots, you have 5 of them, and so forth. All right? So it's this big, long, nasty looking formula to find this. But if we simplify this to our CIS notation, I don't think it will be that bad. So we can rewrite this. We usually write roots using this Greek letter called omega. It looks like a curly W, so that's what we use to indicate roots. So another way to write this formula is omega sub k is equal to the nth root of r, so the nth root of the radius, CIS theta plus 2k pi over n. So the k is referring to which root you're actually working with. So is it the first cube root? Is it the second cube root? Is it the third cube root? And so on. N is, of course, the actual root that you want to take of the number. And so basically what this is going to do is it's going to take all of your roots are going to form a regular polygon in the plane. So we have these equally spaced roots all surrounding the origin. And so actually, if you want to look at the polygon thing, I'll post something on Moodle about that because I think it's pretty cool, especially for those of you that like geometry and stuff. I think you should take a look at that. So check out Moodle for that. I'll have that up in a bit. So anyway, yeah, that's a shorter way to write roots, the root equation. So now let's look at some examples. So just a few more definitions first. So the modulus of each root is the radius. The argument of the first root is theta. And so we repeatedly add 2 pi over n to get the argument of each successive root. Sorry, this should be theta over n. And so basically, like I said, that's what contributes to each root being equally spaced around the origin. And definitely check out the polygon thing if you have time. So for our first example, we want to find the cube roots of the complex number -2 plus 2i. So again, just keep in mind that this is in quadrant 2 because we have a negative x coordinate and a positive y coordinate, and because we want cube roots, we know that n is going to be 3. Okay, so first of all, let's get this number into its polar form. So we need the radius, which is the square root of a squared plus b squared. So we have the square root of negative 2 squared plus positive 2 squared. So we have the square root of 4 plus 4, which is the square root of 8, and we can simplify this to 2 times the square root of 2. So that is the radius. And next, let's find the argument. So we have theta is equal to tangent inverse of negative 2 over positive 2. Well, negative 2 over 2. It doesn't really matter where the negative is. So this is just tangent inverse of negative 1. And so what angle in quadrant 2 has a tangent of negative 1? And the angle that comes to mind is 3 pi over 4. So that is going to be the argument of our number. So if we wanted to write z in polar form, we would get 2 square roots of 2 cis 3 pi over 4. So that is our number in polar form. So now what we want to do is find the cube roots of this number. So if we write down our big equation for our roots, we have the nth root of r, cis theta over n plus 2k pi over n. And I'm only writing it a little bit differently with the fractions split up in that argument because I think it'll make it easier when we actually go to find the other roots. So, let's see, what are we looking at? So, first of all, in this case, we want the cube root, so we'll say that, let's plug in our numbers. So we have w sub k is the cube root of 8, cis theta over 3 plus 2 pi over 3 times k. So that's kind of our general formula in this case for all of our roots. And so we can simplify that a little bit more by saying 2 cis. Let's see, theta is 3 pi over 4. So theta divided by 3 is just pi over 4 plus 2 pi over 3 times k. Okay, so this is a really nice formula now for getting our roots. So the first cube root, omega sub 1, is going to be 2 cis. Actually, let's call it omega sub 0. That'll make our k's work out. So we have omega sub 0 is 2 cis pi over 4 plus 2 pi over 3 times 0. So this just simplifies to 2 cis pi over 4. Wasn't that easy? All right, we have two more roots to find. So omega sub 1 is going to be 2 cis, and to find the next argument of our next root, we're just going to take the previous one and add 2 pi over 3. So if we get common denominators, you get 2 cis, let's see, 12 would be the common denominator, so we get 3 pi over 12 plus 8 pi over 12. So this would be 2 cis 11 pi over 12. So that's our second root. Again, super easy now that we have this in polar form. And finally, our last root would be omega sub 2, which is 2 cis. And now this time we take the 11 pi over 12 and we add 2 pi over 3, which gives us 2 cis 11 pi over 12 plus 8 pi over 12. And if we add that, we get 2 cis 19 pi over 12. And alright, so those are the cube roots of negative 2 plus 2i. So now we want to kind of apply this to solving equations. So let's look at the equation z to the 6th minus 1 is equal to 0. Alright? If we wanted to solve for z, it might seem kind of obvious that we would just want to add 1 to the other side. So we get z to the 6th is equal to 1. But now, if I wanted to solve for z, I would get the 6th root of 1. And while you might think that, oh, well, that's just 1, yes, it is, but this time we're solving over complex numbers and not just real numbers. So we not only want 1 as an answer, but we want all those hidden complex solutions as well. So we can also use our polar form to do this. So what we want to do is change 1 into its polar form. So the radius is going to be a squared plus b squared, and you can kind of think of 1 as 1 plus 0 times I, and that might make it a little easier. So we have 1 squared plus 0 squared, so our radius is just 1. We get the square root of 1, that's 1. Theta is going to be tangent inverse of 0 over 1. So this is just tangent inverse of 0. And so you're thinking about the angle in, well, this isn't really in a quadrant, is it? It's on the x-axis. Yeah, it's on the x-axis, and so we want to say that this is 0. So tangent inverse of 0 is 0. All right. So we have our r, we have our theta. So 1 is equal to 1 CIS 0. Okay, so now that we have the polar form of 1, we can find our roots really easily. So let's just write down our root equation. So we have omega sub k is the 6th root of 1. And so when we say 6th root of 1 there, we're just talking about the real number, so it would be positive 1. Then we have CIS theta over 6 this time, because we're looking at the 6th root plus 2k pi over 6. Okay, so if we plug in our theta, we can simplify this a little more. So we have 1 times the CIS of 0, 0 over 6 is 0, plus pi over 3 times k. Alright, so that is our general solution for all 6 of our roots. So basically what this means is every time we go to a new root, we're just going to add pi over 3 to the argument. So for omega sub 0, we get 1 CIS 0, and that's just 1. That's the real solution that we already knew about. Omega sub 1 is going to be 1 CIS pi over 3. So this one's really nice because we started at 0, so we can just add pi over 3 to each argument. Omega sub 2 is going to be 1 CIS 2 pi over 3. Omega sub 3 is 1 CIS pi, so 2 pi over 3. Add another pi over 3, we get 3 pi over 3, that's just pi. Omega sub 4 is 1 CIS 4 pi over 3. And omega sub 5 is 1 CIS 5 pi over 3. So notice here that if we were to add another pi over 3 and try to go for an omega sub 6, that would end us back at 2 pi, which is the same thing as 0. So that is indeed the last root that we can find. Okay, so that is how you would find the 6th roots of 1. So I bet you didn't know 1 had that many roots, did you? Alright, so that is it on complex numbers. Hopefully that made a little bit of sense. Keep working on the homework. And if y'all have any questions, please let me know.